Okay, so now let's look at another special situation. Suppose m dx plus n dy is equals 0 is given, an exact differential equation, or so we might think. Now, what if in the situation we have that this is in fact not equal to this? Well, if this is the case, then it fails. We can't solve it. There's nothing we can do about it until we readjust. So we multiply an integration constant of both sides. Im dx plus I n dy equals 0. Now, in this regard, we're supposing that the partial derivative of y of Im is equal to the partial derivative of respect to x of In. Now, by the product rule, we have, well, first, we have m partial I partial y plus I partial m partial y equal to partial, we have n partial I partial x plus I partial I, no, sorry, partial n partial x. Now, just to kind of give you a observation, this one's a partial differential equation, and if solving regular differential equations were difficult, this one's maybe a million times worse. So we actually have to impose some conditions. One, suppose that I was dependent on y only, or let's say this, dependent on x only. Then that means that the partial derivative of I is equal to 0 because there's no y terms. This means that we have m partial I partial y plus I partial m partial y equal to n partial I partial x plus I partial n partial y. Now, in this situation, this goes away, gets completely cut out. Now, I want to then move this to the other side. So we're going to get I, and this one's just my, and this one's just nx equal to n partial I partial x. Now, because all this is assumingly dependent on x, we can actually just create ddx, but we'll keep it as it is. Partial I divided by I is equal to the my minus nx divided by n partial x. Because we impose the condition that this is only dependent on x, this can be treated as if it was just a dx. So our first integration constant is the exponential of the integral of my minus nx divided by n dx. This one is only dependent on x. So if we have the situation where we get some kind of y term inside there, then we have a problem. So that was case 1. Now, all this is case 1. Suppose then now we have case 2. I is dependent on, so first one was dependent on x. Now let's say it's dependent on y only, case 2. That as such, partial I partial x is equal to 0. So we write our relation again, partial I partial y plus I partial m partial y equal to n partial I partial x plus I partial n partial x. This one goes to 0, goes away. Now similarly, we can then find the relation given instead now by nx minus my equals to partial I, or m partial I partial y. And we can we can show that this is equal to the exponential of the integral of nx minus my divided by m dy. From over here, this one is now only dependent on y only. So this is dependent on y. So using one of these two forms, I is equal to exponential of my minus nx divided by n, or the integral of it, the integral of it dx, or I is equal to the exponential of the integral of nx minus my divided by m dy. We can correct the exact differential equation, and as such, we just use the same exact methods. As discussed before. So in the event that Clairaut's theorem fails, we have two integration factors that we have to account for. And then sometimes it might not even be doable, in which case we just say not doable. Okay, thank you. Well, actually, I won't do an example problem here, but see, as a challenge for the viewer, I challenge you to see if you can do any kind of problem where Clairaut's theorem fails and see how, by correcting it with an integrating factor, you're able to find an exact differential equation. Until next time, thank you.